have already discussed little L2, the space of square summable sequences. So, I have a sequence x sub I which satisfies I is equal to 1 to n mod xi squared is finite. So, this is a square summable sequence and becomes relevant in the context of quantum mechanics. In fact, we have been looking only at L2 most of the time without saying so, because when I expand a state psi in terms of a basis set phi n, this n is not to be confused with that n. With coefficient Cp, and given that this is an orthonormal basis and that psi is normalized to 1, it implies that summation over p mod Cp squared is 1 and therefore certainly less than infinity. So, the probability amplitudes Cp when expanded in this manner happen to satisfy the requirements of a square summable sequence, and therefore little L2 becomes very important in the context of understanding the framework of quantum mechanics. I also mentioned another space which was the space of square integrable functions defined in the region AB. These would be functions of a real variable x and if they are square integrable functions psi of x, they would satisfy psi star of x, psi of x dx is finite, and a and b could well be minus infinity and infinity respectively. So, this is a kind of direct extrapolation of a square summable sequence. These are square integrable functions of x. So, today I will talk about certain aspects of square integrable functions of x. In other words, we will be discussing the space capital L2 of a comma b. So, square integrable functions. The linear vector space is L2 of a comma b. So, this is what we will talk about today. L2 of a comma b is an example of a separable Hilbert space. So, that means that the space L2 of a comma b has a denumerable infinity or a countable infinity of basis states, and this could be an orthonormal basis. You can always make it an orthonormal basis. Since it is the space of functions, clearly the basis states are functions of x, and any state, any arbitrary state in this linear vector space can be expanded in terms of these basis functions. So, since a and b can take various values, I would like to give certain examples of L2 of a comma b right away. So, let us look at L2 0 comma 1. Now, in this space we can easily check that the basis states, the basis vectors are 1 root 2 cos 2 pi k x and root 2 sin 2 pi k x, where k itself takes values 1, 2, 3 and so on. So, I have a denumerable infinity of basis states, that is an infinity and that is another infinity because k takes various values. This is an orthonormal basis. I have taken care to normalize these basis states to 1 by putting that root 2 there. And how do I see that they are orthogonal to each other? Suppose we did integral 0 to 1 dx, let us consider those two basis states, root 2 cos 2 pi kx. It is trivial to check that that is 0. Similarly, if I took these two basis states 1 and root 2 sin 2 pi kx, that is 0. Root 2 cos 2 pi kx for any k, an integer k, positive integer k, that is also 0. So, they are orthogonal to each other. They can be normalized to 1, indeed they are normalized to 1, because clearly 0 to 1 of 1 times 1 dx is 1, 0 to 1 root 2 cos 2 pi kx for a given k, and so on. The root 2 is important because it's needed to normalize this to 1. So, this is a denumerable infinity of basis states in the linear vector space L2 of 0, 1. So, that is my first example, and all functions in this space can be expanded in terms of these basis states. Let us look at the next example. Let us consider the space L2 of -1, 1. I did mention this in an earlier lecture. The basis states could well be the Legendre polynomials, because -1 to 1 rings a bell. You could choose x to be cos theta, because cos theta goes from -1 to 1. The Legendre polynomials could be chosen as the basis states. So, these are Pn of cos theta. So, my x is cos theta. And they are certainly orthogonal to each other. In terms of the Dirac-Ket notation, the orthogonality property would be this: normalized to 1 and orthogonal. Let us just look at the fact that if n is not equal to m, that is 0, there is no overlap. So, this would simply be Pn of x, Pm of x dx integral over the range -1 to 1 is 2 by 2n plus 1 delta mn. And I mentioned earlier that we could write the completeness relation in this context analogously. Summation over n L sub n Pn of x prime is delta of x minus x prime, and L sub n is 2n plus 1 over 2. So, it forms a complete orthonormal basis. You can expand functions in this space as a linear combination of the Legendre polynomials. This is already well known to students who have studied electrostatics. Take the example of trying to find out the potential far away from a static charge distribution, an arbitrary charge distribution. This is a digression. We recall what we learned from electrostatics. So, you have an arbitrary charge distribution. This is the origin, and it is a uniform volume charge density rho. Let me take a small element here dV, which is at a distance r prime from the origin of coordinates. Now, I want to find out the potential at some point P, which is pretty far away from this arbitrary charge distribution, let us say at a distance r from it. This distance itself is little r. This is r prime. The distance from the origin to dV, which is an elementary charge distribution, an elementary volume of charges. The distance from dV to P, which is where I want to find the potential, is r, and P is assumed to be very far away from this distribution, so that to a first approximation the arbitrary charge distribution looks like a spherical object. And of course from the origin of coordinates to P the distance is little r. So it is clear that the potential at the point P is simply the total charge. Of course there is a 4 pi epsilon 0 r. Now I do a multipole expansion. In the sense I expand this 1 by r in terms of little r and r prime. Now if I did that, it is clear that r squared is little r squared plus r prime squared minus 2 r r prime cos theta, where theta is this angle, that is theta. This angle. Clearly I can simplify this better, and I do the following. So I have r squared is little r squared plus r prime squared minus 2 r r prime cos theta. Pull out an r squared and write this as 1 plus r prime squared by r squared minus 2 r prime by r cos theta. It is very clear that r prime is a very small distance compared to r, because P is pretty far away from the charge distribution, and therefore the expansion is done in powers of r prime by r. I could call this epsilon. Now this epsilon is a function of r prime by r and cos theta. So I have r squared is little r squared 1 plus epsilon, and therefore I need 1 by r, that is what figures in the potential V of P. So 1 by r is 1 by little r 1 plus epsilon to the minus half, and then this expansion is in powers of epsilon, alternating positive and negative, and this is what I have. Now I could well go back and write out epsilon and substitute for 1 by r, and I find that 1 by r, what is, I simplify this by putting in the value of epsilon, putting in epsilon in terms of r prime by r and cos theta. I find that 1 by r is this 1 by r, and this series is summation n equals 0 to infinity r prime by r to the n power of n Pn cos theta. So already you see there is an example from electrostatics where the potential due to an arbitrary charge distribution pretty far away from the location of the charge distribution is expanded in this basis. The first term in the basis turns out to be the monopole contribution, the second term is the dipole contribution, the third term is the quadrupole contribution, and so on. So it is in this very same spirit that in quantum mechanics, if you have a linear vector space L2 of minus 1 1, you could use Pn of cos theta as the basis, and functions of cos theta, any arbitrary function of cos theta, can be expanded in terms of the Pn cos thetas. In fact, it turns out that Pn cos theta figures in quantum mechanics in the study of orbital angular momentum. That is a situation where one wants to study orbital angular momentum, obviously in physical space because it is r cross p, and that would mean using coordinates x, y, z, or if you wish in spherical polar coordinates the radial coordinate r, theta and phi. And then if you write the state of the system, the eigenstate of orbital angular momentum as a function of r, theta and phi, the dependence on theta can be expanded in terms of Pn cos thetas. So that is one place in quantum mechanics where Pn cos theta comes in, and we will certainly look at the problem of orbital angular momentum in a subsequent lecture. The third example that I wish to consider for the space of square integrable functions is L2 minus infinity infinity. I did mention this earlier. In this case, one could use the Hermite polynomials. The Hermite polynomials as the basis functions Hn of x, and their orthonormality property involves a Gaussian measure e to the minus x squared Hn of x Hm of x dx is some a n delta mn. They form a complete basis in L2 minus infinity infinity. The Hns figure in quantum mechanics in the context of the simple harmonic oscillator, a problem which has already been studied by us in the abstract Ket notation, where we had the energy eigenstates of the oscillator represented by n and so on. You will recall that these were eigenstates of the operator A dagger A with eigenvalue n, and when n is 0 it represents the ground state of the oscillator, n is 1 is the first excited state, and so on. Equivalently, in quantum optics, n is 0 would refer to the 0 photon state, n is 1 to the 1 photon state, and so on. Now if I represent this abstract Ket in function space, the relevant function space turns out to be L2 of minus infinity infinity, and the various basis states in function space, which I would represent by psi n of x, where x is position, turns out to be essentially the Hermite polynomials. So that is another example. Again, we will study this example. We will redo the oscillator problem in the Schrodinger formalism, where basically the function space becomes important, and we will study the properties of the energy eigenstates of the oscillator in terms of the behavior of the Hermite polynomials. The last example that I want to point out today is the space L2 0 comma infinity out there. It is clear that the argument in a physical context should be the modulus of a vector, and in this case we use the Laguerre polynomials as the basis states. That is an example. You could use the Laguerre polynomials Ln of x and this appears in the context of the hydrogen atom problem, for instance, where once more if the hydrogen atom is considered in a three-dimensional space in spherical polar coordinates, this r obviously takes value 0 to infinity, and the radial wave function or the state of the system expressed in terms of the radial coordinates can be expanded in terms of the Laguerre polynomials, which forms an orthonormal basis in the space L2 0 comma infinity. So these are various examples where function spaces are very important. In particular, the square integrable functions are very important in studying various quantum mechanics problems. I want to draw attention to a very important fact in this context. Suppose you look at the various Legendre polynomials, for instance. So P0 of cos theta is 1, P1 of cos theta is cos theta itself. So let me call it x. So P0 of x is 1, P1 of x is x, P2 of x is 3x squared minus 1 by 2 and so on. You would find that these are odd functions of x, p1, p3, p5 and so on, and p0, p2, p4 are even functions of x. Similarly, if you look at these are the Legendre polynomials. Look at the Hermite polynomials. Hermite polynomials also, h0 of x is 1, h1 of x is 2x, h2 of x is 4x squared minus 2. Once more, h0, h2 are even functions of x, and h1, h3 etc. are odd functions of x. Now if you look at the Laguerre polynomials, same thing. This is Hermite. L0 is 1, L1 of x is an odd function of x. So there is an x, and that just becomes L1 of x. When x goes to minus x, it becomes 1 plus x. Let us forget this. As far as x is concerned, it is an odd function. And L2 of x is x squared minus 4x plus 2 apart from a constant. So that is a quadratic in x, and so on. So it alternates, even function. The highest power of x is odd in the case of L1, L3 and so on, and the lowest power and the highest power of x in the case of L0, L2 and so on is an even function of x. The highest power is even. Now this becomes very important, because if you look at the Hermite polynomials, for instance, here, so if you look at one-dimensional oscillator, the simple harmonic oscillator, where I have mentioned that the Hermite polynomials become important, you find that the wave function has a definite parity. In other words, I define a parity operator which basically takes x to minus x. That is the job of the parity operator. So when the operator, if you wish I put a cap on it, acts on a function in the space L2 minus infinity, infinity, which is the relevant linear vector space for the simple harmonic oscillator, this takes it to psi of minus x. Of course, if the parity operator were to act in 3 dimensions, then it takes x, y, z to minus x minus y minus z. Equivalently, it takes r theta phi to r, theta goes to pi minus theta, and phi goes to pi plus phi. So any function psi of x, y, z under the action of the parity operator becomes psi of minus x minus y minus z, and so on. So you find that the HNs, which are essentially the energy eigenstates or the eigenbases of the simple harmonic oscillator, are definite parity states. So from what I have said earlier, one now suspects that these states are simultaneous eigenstates of the parity operator and the Hamiltonian. And indeed that is what happens, and I will comment on this later, so that the states ket n of the oscillator, which I spoke about earlier, when represented as functions of x, because there is only one argument here because it is a one-dimensional oscillator, turn out to have definite parity, and they are also simultaneous eigenstates of energy and the parity operator. So the parity operator and the Hamiltonian commute in the case of the simple harmonic oscillator, a matter which will be studied in much detail in a subsequent lecture. So now, as I have already indicated, most times by x we mean position. not always true, but quite often. So, the argument x turns out to be relevant to position, and in the position representation you have to define operator functions of x which will act on the state psi of x, which itself is an arbitrary state expanded in terms of the basis states that we have selected. Could be the Laguerre polynomials, could be the Legendre polynomials, could be the Hermite polynomials, depends on the space. The simplest operator function of x that I can think of is x itself. There is no need to put the cap. So, in the position representation, the position operator, this is a very crucial point, is x. I should use the same x. It has position eigenstates. The job of the operator is simply to pull out the position eigenvalue. But unlike the earlier examples we spoke about, now we have moved to a more complicated situation where x is a continuous real variable which takes values in the range a to b, and therefore the position basis or the eigenbasis of the position operator happens to be a continuous basis. Since it is a continuous basis, we cannot imagine that it can be represented as a column vector with discrete entries, nor can we imagine that the operator, the position operator, can be represented by a matrix which has got distinct rows and columns. In fact, the rows become continuous, the columns become continuous, and that is why we call it an operator. Can't do better than that. This is the position operator, and in the position representation, the operator itself can be represented by x. There are other linear operators in this position space. An example would be d by dx. Clearly, this is a linear operator, because if it acts on, say, C1 psi 1 of x plus C2 psi 2 of x, where psi 1 of x and psi 2 of x are functions in this space and C1 and C2 are constants, that is just d by dx psi 1 of x plus C2 d by dx psi 2 of x. So, it is a linear operator, and this operator becomes important. To begin with, operators need not commute with each other, because if we look at x d by dx acting on psi of x, since they are linear operators, first d by dx acts on psi of x and then x acts on psi of x. Now, an important point to remember is that operators do not commute, and so if I found the action of x d by dx on the function psi of x, that is not the same as d by dx x psi of x, because this is simply x d psi by dx, whereas this is psi of x plus x d psi by dx. That bracket, that makes the crucial difference, and therefore operators in general do not commute. But this relation that I have seen here, this example, tells me something. We know that the position and momentum operators do not commute, and in one dimension xp is IH cross identity, and therefore P can well be represented in the position representation as minus IH cross d by dx, and I am doing one dimensions. There is only one variable x. So if we check now, xp acting on psi of x is minus IH cross x d by dx psi of x. Px acting on psi of x is minus I by IH cross psi of x plus x d psi of x by dx. And therefore, the commutator of x with p acting on an arbitrary state psi of x gives me IH cross psi of x, or xp is equal to IH cross. So in the position representation, the momentum operator has to be represented as an operator function of x, and it is written as minus IH cross d by dx in 3 dimensions. One deals with x, y, and z, and therefore the momentum operator, if you wish, I'll put a hat there, is minus IH cross E sub x d by dx plus E sub y d by dy plus E sub z d by dz, or minus IH cross del. This is in 3 dimensions, and this is the manner in which we represent the momentum operator in the position basis, in the position representation. Now similarly, I could think of working with states in the momentum space. What I mean is, I could think of the argument as momentum, I certainly know how to go from functions of position to functions of momentum through the Fourier transform. By which psi of x goes to psi tilde of p, which is a state in the momentum space. Obviously, operators acting on psi tilde of p should be functions of p, and even as we represented the position operator by just x in the position representation, the momentum operator acting on the momentum basis simply picks out the momentum eigenvalue, and this is a continuous basis again. You will recall that p changes continuously. It's a continuous variable, it's a real variable, and the momentum operator in the momentum representation could be well represented by p itself. These are conjugate representations in the sense that I can go from one basis, the position basis, to the momentum basis by a Fourier transform. So in the momentum representation, momentum itself is given by the label p, the momentum operator, and I need to write the position operator in terms of p as an operator function of p. We can easily check that the position operator in the momentum basis is plus IH cross d by dp. Let us work out the commutator. xp acting on psi tilde of p is expected to give IH cross psi tilde of p, because it is like the identity operator acting on psi tilde of p apart from I and H cross. So we can check that out. So where we are looking at functions of momentum as the states in the linear vector space, this amounts to writing IH cross d by dp acting on p psi tilde of p, and that has 2 terms, IH cross psi tilde of p plus p IH cross p d psi tilde of p by dp. This is as far as xp is concerned. Now px psi tilde of p is IH cross p d psi tilde of p by dp, and therefore between the two of them the commutation relation is satisfied. This term cancels with that, leaving behind IH cross cycle tau of P. So in the momentum representation, which is another important representation, that means I would like to expand the states and write the operators as functions of momentum, and the states are expanded in terms of the momentum basis functions, psi tilde of P, for instance. I find that in the position representation, momentum is represented by minus IH cross del, and this is in the position representation, where x itself is x and P is minus IH cross del. This is in the position representation. So in one dimensions, P is simply minus IH cross d by dx. And in the momentum representation, where my basis states are a continuous basis labeled by the momentum values P, these are eigenstates of the momentum operator, x is represented by plus IH cross d by dP, and P itself is simply the momentum value P. These are conjugate representations. We may choose to work in the position representation or in the momentum representation if necessary. When we talk about systems in space, like a hydrogen atom and its coordinates, or a harmonic oscillator at a certain point in space or moving in space, we need to work with functions of x, where x represents the space variable, and so on. Now finally, I want to go to the harmonic oscillator problem and illustrate a certain point. The Hamiltonian of the oscillator, one dimensional oscillator, the simple harmonic oscillator, is p squared by 2m plus half m omega squared x squared. Written in the position representation, this would be minus IH cross d by dx the whole squared, 1 by 2m multiplies that, plus half m omega squared x squared, which is the same as minus h cross squared by 2m d2 by dx squared plus half m omega squared x squared. And if we are looking out for position eigenstates, energy eigenstates, h psi n is E n psi n, certainly h has to be written in this fashion, and psi n has to be written as functions of position. The n takes values 0 to infinity because it is a denumerable infinite basis set, and the psi itself has to be written as a function of position. So that brings us to a very important point. How do you represent psi of x in terms of the Dirac notation, using the Dirac notation? Suppose you have an orthonormal basis, and suppose the basis is also complete. So I write psi n psi m is delta nm, and suppose the basis is also complete. In short form, I would have written this earlier as n is identity. Look at the position basis. The position basis is a continuous basis denoted by x. The label x takes continuous values. Then certainly this completeness relation translates to integral dx x is identity. And therefore, if I were to talk about a function of x, in the abstract notation I could have well written psi summation over n psi n is identity. I can introduce a complete set of states. I would like to write psi in the position basis and therefore I could do an integral dx sin x x sin equals identity, because this was anyway identity and this would also be identity. I want to now write psi n psi m is delta nm. For the same value of n and m, I have psi equals 1, which shows that it is normalized to 1. I can do the following thing. I can write this as integral dx, introducing a complete set of states, I have simply introduced integral dx, this operator x because that object was 1. Recall that integral dx x is identity. But I know the following. This is to be understood as psi star psi star of x psi of x dx integral over x is 1. It's simply 1, not the identity operator, is 1. Therefore, I write psi of x as the object x psi. In other words, I have written the state psi in the position representation. This implies that psi star of x is psi x. I use bra psi ket x for psi star of x. So by just introducing a complete set of states, I have understood what the notation is in terms of the Dirac notation. Psi of x, which is a function of x, is x psi. Psi star of x is therefore psi x. Similarly, if I were looking at the momentum representation, psi tilde of p is p psi. Psi star tilde of p, which is the complex conjugate, is p psi tilde p. So this is the way we represent functions, or as functions of position or as functions of momentum. This is a very crucial input. And now if you return to the harmonic oscillator, this Hamiltonian acts, I should really be writing in the position representation, h acts on psi n of x to give me E n psi n of x, where n takes value 0, 1, 2, 3 and so on. So let us look at that. Look at the ground state. You will recall that the ground state was represented by ket 0 and the annihilation operator destroyed the ground state. But we also know that x was a plus a dagger by root 2, which was dimensionless, with a root of h cross by m omega, which had dimensions that were appropriate, and p is 1 by root of m omega h cross. These are operators, a minus a dagger by root 2i. Now suppose for convenience, just to illustrate the point, I set m equals omega equals h cross equals 1, then I can see that x is a plus a dagger, root 2x is a plus a dagger, root 2i p is a minus a dagger. And the equation for the ground state, a on ket 0 is 0, simply translates to the following. A itself is root 2x plus I times minus IH cross d by dx. It is just x plus minus IH cross d by dx. because 2a was root 2 times this. So, give or take a half, and a on ket 0 equals 0 just becomes, turns out to be psi 0 of x acted upon by this operator is 0. That implies, and I have set h cross equals 1, so I can get rid of that there, and that tells me that d by dx plus x psi 0 of x equals 0. The ground state of the oscillator in the position representation is clear that the solution is essentially e to the minus x squared by 2, which is a Gaussian. So, the Gaussian is a minimum uncertainty state. We have already shown that the ground state of the oscillator is a minimum uncertainty state, and we have just now seen that the ground state of the oscillator can be represented by a Gaussian function of x. So, this is an example of a wave function or a state represented as a function of x. The relevant linear vector space is L2 of minus infinity infinity in this problem, and the ground state happens to be a Gaussian. Now, we have seen that the Gaussian is a minimum uncertainty state. It is a different matter that we can check that out explicitly once more for ourselves, and indeed the Gaussian turns out to be minimum in delta x and minimum in delta p. There are certain very interesting and important differences between finite dimensional vector spaces and infinite dimensional vector spaces, particularly in the context of bounded and unbounded operators. So, I would look at L2 of minus infinity infinity more closely in a subsequent lecture, and talk about bounded and unbounded operators in this context. Some very important operators turn out to be unbounded operators in this framework. The function space itself becomes very important in discussing the Schrodinger formalism of quantum mechanics, that is wave mechanics, which is what we will take up shortly.